Show by the principle of mathematical induction that for all n belonging to the set of natural number n, this expression is a positive integer. Now, before beginning, so let me clarify here that we do not have to prove that this expression is an integer. This already is an integer. All we have to do here is use the principle of mathematical induction and show that this is a true statement. That means any natural number that we pick up, here n is a natural number, any natural number that we pick up, this integer, the value that we get is always going to be a positive integer. So let us now begin. So our first task will be to convert this statement into a mathematical statement. So what we'll do, we'll suppose that let P of n be the statement given by P of n such that we have n raised to the power of 7 whole divided by 7 added to n raised to the power of 5 whole divided by 5 added to n cubed over 3 added to n squared over 2 minus 37n over 210. It's this is a positive integer. So this is what we have done. We have converted our given statement into a mathematical statement denoted by P of n. And we're going to denote it by 1. So let this be number 1, the statement number 1. Now in order to show that this is a true statement, what we'll do, first we will verify if it is true for n equals to 1 or not. So if we consider n equals to 1, that means the first natural number 1, then our statement is going to become P of 1 such that we have 1 over 7. All we have to do is replace the value of n with 1 in the entire expression. That gives us 1 over 7 added to 1 over 5 added to 1 over 3 plus 1 over 2 minus 37 over 210. So let us compute this value. That's going to give us 1. And we know 1 is definitely a positive integer. So here we can say here that our state P of n, the original statement P of n, this is going to be a true statement for n equals to 1. So this is valid for the first natural number 1. However, we'll also have to show that it is valid for other natural numbers as well. So instead of taking n equals to 2, 3, 4, what we'll do, we'll take a general value. So let's say we take let n be equals to m, and we will suppose that the statement P of m is also a true statement. Now if P of m is a true statement, with essence what we are saying here, the statement P of m such that we'll take the original statement P of n, replace the n with m. That gives us m raised to the power of 7 over 7 added to m raised to the power of 5 divided by 5 added to m cubed over 3 added to m squared over 2 minus 37m over 210. So here we're saying that this expression is a positive integer. So we are considering this to be a true statement. We're assuming that it's a true statement. And if this is a true statement, then using this statement, we will have to show that the next consecutive integer that we take, or next consecutive natural number that we take, which is going to be m plus 1, P of m plus 1 is also true. This is also true. This is what we'll have to show. Now what is P of m plus 1? P of m plus 1, that's simply, we'll take this expression that is P of m, we'll take the statement P of m, and we are going to replace m with m plus 1. So we have m plus 1 whole raised to the power of 7 divided by 7 added to m plus 1 whole raised to the power of 5 divided by 5 added to m plus 1 whole cubed divided by 5 added to m plus 1 whole squared divided by 2 minus 37 multiplied to m plus 1 whole divided by 210. So we have to show that this is also a true statement. That means this is a positive integer. So this is our goal, to show that the statement P of m plus 1, that means we have the expression which is given by this particular expression, this is a positive integer. This is what we need to show. Now how do we show that this is a true statement? So here we'll be taking the help of, let's call this as statement number 2, the statement P of m, and P of m plus 1 as statement number 3. Now from statement number 2, since we have already considered that P of m is a true statement, so here we will suppose that let P m raised to the power of 7 over 7 added to m raised to the power of 5 divided by 5 added to m raised to the power of 3 divided by 3 plus m squared over 2 minus 37m divided by 210. We'll suppose this entire expression is denoted by lambda, where we are supposing that lambda is nothing but a positive integer z plus. Okay, so we're going to take this help, so let's call it number 4. We're going to take this help and we will show that P of m plus 1 is a true statement. So how do we do that? So first we will consider the expression given by P of m plus 1. Our goal will be to expand each of the expression in the numerator, and once we have the expanded form, we can take the help of number 4, equation number 4, to show that this is a true statement. So let's first expand each of the terms. Now that we have the expanded form, so what we'll do, we'll take the first term of each of the expanded terms. So we will take m raised to the power of 7 over 7 added to m raised to the power of 5 over 5, then m squared over 2, we also have here m cubed over 3, and minus 37m over 210. So let's do that. So we now have m raised to the power of 7 over 7 added to m raised to the power of 5 divided by 5 plus m cubed over 3 added to m squared over 2 minus 37m over 210. Okay, so this is going to be one single term. Now the reason why we're combining only these terms, because according to equation number 4 we can replace this with lambda. Fine, then what we'll do, we'll take the last term of each of the expansions. So we have 1 over 5 added to, so here we have 1 over 7 as well, 1 over 7 added to 1 over 5 plus 1 over 3 plus 1 over 2 minus 37 over 210, and then we have the remaining terms. So here are this entire expression that can be replaced with lambda. Then when we add up these fractions, that's going to give us 1 added to the remaining terms, which is going to be some some integer value. So that means we have one integer added to 1 plus lambda, so that's also going to give us some integer value. We don't actually have to worry about the value of that integer. We only had to show this entire expression as some integer, and here it's definitely going to be a positive integer. That means we have now showed that hence the statement P of m plus 1 is a true statement. This is a true statement. If this is a true statement, then we can generalize and finally say that P of n, that original statement, this is also true. P of n is also going to be true statement, and it is going to be true for all values of n belonging to the set of natural numbers. So that means by the principle of mathematical induction, we have verified that this expression is indeed a positive integer for any values of n that we take, as long as n is a natural number.